Welcome to the note sets for the course. I hope you find that this is a useful tool that can assist you in supplementing the readings for the course as well as the homework problems. And we're going to start at the beginning of the course with section 1.1, Systems of Linear Equations. A linear equation is an equation of the form a sub 1 times x sub 1 plus a sub 2 times x sub 2, etc. up through a sub n times x sub n equals some constant b. Now these equations come in all sorts of forms here. There are two equations listed below that aren't necessarily in the linear equation form, at least at first glance, but upon rearrangement, adding the same quantity to both sides, subtracting the same quantity from both sides, we can get them in the form of the linear equation as in the definition. For example, with the equation 4x1 minus 5x sub 2 plus 2 equals x sub 1, if we subtract x sub 1 from both sides and then subtract 2 from both sides, we take that equation and get a new one that's in the same form as the definition. Also on the equation x sub 2 equals 2 times the quantity square root of 6 minus x sub 1 added to the quantity x sub 3, if we distribute the 2, add 2x sub 1 to both sides, and subtract x sub 3 from both sides, we take the equation that's given and get one rearranged so that it's in the same form as the definition. Now there are some equations that no matter how hard you work, you cannot get into the form of a linear equation as in the definition, and we see two here down at the bottom. The first one's not going to be a linear equation because you have the presence of the x1 times x2 term on the right hand side, and then the other equation is not going to be linear because of the presence of the square root of x sub 1, which cannot be made into a linear equation. A system of linear equations is a collection of one or more of the aforementioned linear equations that we saw in the last slide, which involves the same set of variables throughout. For example, if you had a set of equations, each of which used the variables x sub 1 through x sub n. A solution to a system of linear equations is going to be a set of numbers that when you plug them in for the variables, gets plugged into the equations in such a way that each of the equations in the system of equations becomes a true statement. Let's look at some examples where we have systems of two equations in two variables. For our first one here, we have the system of equations x sub 1 plus x sub 2 equals 10, and the equation negative x sub 1 plus x sub 2 equals 0. The points on each line are the solutions to each equation, and if we're going to have a solution to the entire system, it's going to have to be a point that sits on all the lines. And here there's only one such point, the point where the two lines intersect. So there would be a single unique solution to this system of equations. Now if the solutions to a system of equations here are the points that sit on both lines, when we have a system like this that involves two parallel lines, there are no points that sit on both lines, and therefore there are no solutions that satisfy both of the equations in this system. So there is no solution to this particular system of equations. And if we should end up with a system of equations where both equations were giving us the same line, then any point that sits on both of those lines, namely any point from either one of those lines, would be a solution. And so we'd have an infinite number of solutions to this type of system of equations. If we go a little bit further here, we can name these different situations. When the two lines intersect in a point, it's called a consistent system. In fact, it's a consistent system with independent equations. In the second scenario with the parallel lines, it's an inconsistent system. And in the third scenario, where both equations give us the same line, it's a consistent system, but the two equations are said to be dependent. Once again, the two systems in that one are said to be dependent. The situation when we have three equations in three variables or three unknowns is similar to what we had in the situation with two equations and two unknowns. You're looking for the points that simultaneously sit on multiple planes, all three planes. And there are different possibilities that can occur. It could be that the three planes have a single point in common, so there would be a unique solution to that type of system. It could also occur that the three planes have more than one point in common, in which case you'd have an infinite number of solutions because they would share a common line. And there would be an infinite number of points or an infinite number of solutions from that line. Or it could be that there were planes such that of the three planes, there were no points common to all three. And in that situation, there would be no solution to the system of equations. So a big part of linear algebra is, finding the sets of solutions to a linear system of equations. And even more important, we'll spend lots of time studying equivalent systems. That is, there are oftentimes two sets of systems of equations that have the same solution set. And there are various connections among such systems, various steps we can take to convert one system into another such that the systems have the same solution set. And so we're going to look at the types of transformations that we can do to get from one system to another while preserving the same solution set throughout. So this is best illustrated with an example. So let's take a quick look here at the strategy for solving a system of equations. If we can replace one system with another that makes it easier to solve, then we're working things in the right direction. So imagine that we have a system of equations like this one. X sub 1 minus 2x sub 2 equals negative 1. Negative x sub 1 plus 3x sub 2 equals 3. We'd like to know values for x1 and x2 that make both equations simultaneously true. It turns out that one of the steps that preserves the solution set to a system is to add one row to another. So if I were to take the first row of this equation and add it to the second row, and thereby create a new second row, I'd get an equivalent system. I'll leave the first line intact, but then I'll add the first line to the second line to create a new second line. And now my system of equations becomes x sub 1 minus 2x sub 2 equals negative 1. Top line stays the same, but in adding the two lines together, the x sub 1 variable cancels out, and my second equation becomes x sub 2 equals 2. And you probably know what can be done at this point. Essentially you can go in and do back substitution. Alternately, you could add a multiple of the second line to the first one like we just did. If I were to do that, if I were to double the bottom line and add it to the top line, my system of equations would be x sub 1 equals 3, x sub 2 equals 2. Okay. Now here's what was happening throughout from a picture point of view. When we did this, when I added one row to another, it did change the equation. However, it preserved the solution set. If you can see here, the 0.32 was a solution throughout as I did these algebraic manipulations. The first set of equations, the second set of equations, the third set of equations, on all three pictures, the 0.32 is the point of overlap. So this is the type of algebraic manipulation that can occur, adding a multiple of one row to another. It preserves the solution to your system of equations. Rather than working directly at all times with the actual system of equations, it'll often be more expedient to use a matrix that represents your system of equations instead. There are a couple of ways to do this. One is to use a coefficient matrix, which is a matrix here. It's a 2 by 2 grid that takes the coefficients from the left-hand side. You notice the coefficients in the top equation, coefficient of x sub 1 is 1, the coefficient of x sub 2 is negative 2. For the bottom equation, the coefficient of x sub 1 is negative 1, and the coefficient of x sub 2 is 3. So if I take those numbers and put them into a matrix, you get this coefficient matrix. Now, an important part of that is that the system of equations be in standard form. You have all the x sub 1 terms first, all the x sub 2 terms second, the equal signs lining up, and then the constant terms on the right-hand side. We could go one step further and create an augmented matrix where we not only include the coefficients, but then include a third column here. You can see that third column of negative 1 and 3, where the negative 1 and 3 were just the constants that were on the right-hand side of the equal sign. We can work with an augmented matrix and find the solution much in the same way as we would for a system of equations. It's just that instead of having to write the system of equations at all times, all we really have to work with here is the coefficients in that augmented matrix. So let's look at the steps that we just did in that last example from the last slide. Let's look at it from a matrix point of view. Our first step was to take the second line and add it to the first line and create a new second line. Let me say that another way. What we really did was we took the first line, added it to the second line, and created a new second line. We left the first line alone. What would that look like from a matrix point of view? Take the first line, add it to the second line, and while leaving the first line alone, create a new second line. So the first line of my new augmented matrix is still going to be 1, negative 2, negative 1. But my second row in the augmented matrix is now going to be 0, 1, 2, once I add the first row to that second row. You can see that my new augmented matrix is exactly the augmented matrix that we would have created for that intermediate system of equations that we worked with in the last slide. After we added the first equation to the second one, we ended up with a new second line of x sub 2 equals 2, and that's a perfect match for the new second row of our augmented matrix. Now, when we did this example from the system of equations point of view, what we did at this point was we took the second line, doubled it, and added it to the first line. Let's do that from a matrix point of view. Take the second line, double it so that it's 0, 2, 4, and add it to the first line. Okay, double that second line, and then take that new quantity that's doubled, go up and add it to the first line, and create a new first line, leaving the second line alone. My new first line here will be 1, 0, 3, 0, 1, 2, for the second row stays the same. But at this point, you can see that the matrix here, the augmented matrix 1, 0, 3, 0, 1, 2, that augmented matrix corresponds perfectly with the solution that we had in our last slide. Because what you're saying in that augmented matrix is that you have 1 x sub 1 added to 0 x sub 2's being equal to 3. And then the second row of that augmented matrix is telling you that 0 x sub 1's plus 1 x sub 2 equals 2, which is exactly what the system of equations right next to it is saying. So there's this very direct correspondence between augmented matrices and the systems of equations that they represent. That right-hand column of the augmented matrix is the solution to our system of equations. X sub 1 is 3, x sub 2 is 2. What we want to do now is we want to take a look at the three types of algebraic manipulation that we can perform on a system of equations, or equivalently that we can perform on an augmented matrix, where we preserve the solution set to the system of equations. So we can do these three things to an augmented matrix without changing in any way, shape, or form the solution set to that system of equations. So here are the three operations that you're allowed to do. You're allowed to do row replacement, where you add a multiple of one row to another row, creating a new row. You're allowed to interchange two rows. And you are allowed to take a row and multiply it by a non-zero constant. You can perform any of these three algebraic manipulations to a system of equations without changing the solution to your system. Row equivalence. Two matrices are said to be row equivalent matrices when one matrix can be transformed into the other matrix by a sequence of elementary row operations. That is, those three elementary row operations, row replacement, row interchange, and row scaling, that we mentioned on the previous slide. And of course, the key point that we've been hammering all along is that any of these operations that produce these row equivalent matrices, any of those operations preserve the solution to the system of equations. Let's expand our repertoire a little bit here and look at a 3x3 system of equations where you have three equations with three variables. We've gotten it in standard form so that the x sub 1, x sub 2, x sub 3 variables, as well as the equal sign and the constants, they all line up. And not only are we going to work on this system of equations, but we're going to do it side by side with the augmented matrix, so you can see how it works both ways. We're going to perform elementary row operations to construct a solution to this system of equations. And hopefully along the way here we can point out the strategies that are necessary to get through this type of problem. Okay, so where we want to start here is we want to start on that first column. To get a solution to this system of equations, what we would like to have inside that red oval is we'd like to have a 1, a 0, and a 0, where we currently have a 1, a 0, and a negative 4. So we've really got 2/3 of what we'd like to have right there. But we've got to go a little bit further to get it so that it's really going to be in the ideal form for getting a solution. And so what we can do here is, well, we can do an elementary row operation to help ourselves out. We'd like to have a 0 where there's currently a negative 4. How can we adjust that? Well, you can add multiples of one row to another. So what we're going to propose to do here is to take a multiple of the first row and add it to the third row. What would be the ideal multiple to choose? Well, let's do 4 times the first row. Because if we do 4 times the first row and bring that down and add it to the third row, when we add the negative 4 and the positive 4, we're going to get a 0, which is really what we'd like to have to start out here. And the rest of the entries there, it's going to be what it is, that's fine. But we really want to have a 0 where there's currently that negative 4. So add those together and we're going to get a new third row of 0, negative 3, 13, and negative 9. So the first row stays the same, the second row stays the same, but we get a new third row after we add 4 times the first row to the original third row. Now, we'd like to have a 1 in the second row where there's currently a 2. We still want to have a 0 to the left of it, but we'd like to have a 1 where there's currently a 2. And since all those entries are essentially even numbers, we can get away with multiplying that row by a half, or equivalently dividing the entire row by 2. When we do that, we get a new second row of 0, 1, negative 4, and 4. We leave the first row the same, we leave the third row the same. but we multiply the second row by a half. Now we're in good shape. We've got that first column, which is 1, 0, 0. We like that. And in the second column, we've got a 1 in the second entry, which we also like. What we'd like to have further in that second column is we'd like to have zeros where the -2 and the -3 currently sit. And we're going to take steps to get that shortly. So looking in that second column there, we have a 1, that's perfect. We like that entry. We'd like to have a 0 where there's currently a -2, and we'd like to have a 0 where there's currently that -3. We said that we'd like to have a 0 where that -2 is, and we'd like to have a 0 where that -3 is, and we can take steps to turn those into zeros. And one such step would be to take a multiple of the second row and add it to the third row. Now the appropriate multiple to use would be to take 3 times the second row and move it down and add it to the third row. Because when we add the 3 and the -3, we're going to get a 0 in that entry, which is perfect. So going forward with that, we're going to get a new system here where the third row is 0, 0, 1, 3. Furthermore now, we've got a pretty nice third row here. In fact, we have a triangle here where you have sort of 1s on the diagonal and 0s below it, and that's a terrific setup to work from. Because now at this point what we can do is we can add the third row in appropriate multiples to the second and first row to create zeros in the third column. And then we can go to that second column and put a 0 where there's currently a -2. But starting with this triangle is a fantastic start here. And see, what we're going to do now is we're going to take multiples of the third row and add them to the second row and the first row. Okay. For starters, we could take 0, 0, 4, 12, move that up, and add it to the second row. When we do that, we get a new second row. That new second row is going to be 0, 1, 0, 16. And you can see, if you look at this in algebraic form, you can see that the second equation and the third equation are done. I mean, you've solved that third equation for x3. You've solved the second equation for x2. x2 is 16, x3 is 3. All we need now is a solution for x1. And to get that, what we'll do is we'll take an appropriate multiple of the second row and add it to the first row. And we're going to do that on our next slide. So to finish this problem off, we're going to take a multiple of the second row and add it to the first row to get a 0 where there's currently that -2. Let's move that up there, add the first row to that multiple of the second row, and we get a new first row that's going to be 1, 0, 0, 29. And now we have a solution to our system. X sub 1 is 29, x sub 2 is 16, x sub 3 is 3. You can see that there was a particular form that we like to have in this augmented matrix. There's sort of a 3 by 3 grid there in that augmented matrix. If we ignore the leftmost column, if we ignore the rightmost column, if we ignore the 29, 16, and 3, if we just cover that up for the moment and look at the rest, the other 3 by 3 grid of entries, it says 1, 0, 0, 0, 1, 0, 0, 0, 1. There's a pattern there of 1s on a diagonal and 0s everywhere else. That's going to become a very, very common theme, and you're going to see that particular pattern show up in a lot of places. We got a solution to this system of x sub 1 being 29, x sub 2 being 16, and x sub 3 being 3. And we can, of course, check that this is a solution to the system of equations by plugging in 29, 16, and 3 and making sure that we get a true statement out of each equation. when we plug it in, we do in fact get a solution to the system of equations. When we put in 29, 16, and 3 into that first equation, you get 29 minus 32 plus 3 equals 0, which is true. When you put in 16 and 3 for that second equation, you get 32 minus 24 equals 8, which is again true. And when we plug in 29, 16, and 3 into that third equation, 29 times negative 4 is going to be negative 116. 16 times 5 is going to be 80. 9 times 3 is 27. And when you put that together, you get negative 116 plus 80 plus 27 equals negative 9, which you can check, and which indeed is true. There are two fundamental questions that are going to arise when you have a system of equations. The first question is the question of existence. Does there exist a solution? Is your particular system of equations consistent enough that you can find at least one solution to it? And then the second fundamental question is, if you can find at least one solution, is it the only solution? Or are there other possible solutions out there? So the one question is, does there exist a solution? And if there's a solution, is it the only one? Those are the two main questions we're trying to consider. In our example that we worked out with the row operations, if we asked ourselves the question about consistency, is there going to be a solution? There was a certain point in the algorithmic operations where we knew we were going to have a solution. And that point in the solution was when we could have identified that triangle where we had ones on the diagonal and zeros below it. Because at that point we knew by getting a solution for x sub 3 that we could put x sub 3 into the equation above it and get an equation for x sub 2. And then once we got x sub 2, we could put x sub 2 and x sub 3 into the equation above it and get a solution for x sub 1. So once we had that triangle with ones on the diagonal and zeros below it, we knew that the system was going to be both consistent and unique. Suppose we took a different system and asked ourselves those two main questions. Number one, is there a solution? And number two, if there's a solution, is it unique? Suppose we had the system of equations 3x sub 2 minus 6x sub 3 equals 8, x sub 1 minus 2x sub 2 plus 3x sub 3 equals negative 1, and then finally 5x sub 1 minus 7x sub 2 plus 9x sub 3 equals 0. Take that system of equations, make the augmented matrix. Now working below the line there are some steps that we're going to take to row reduce using our three allowable operations to try to make that system a little bit more manageable. And so what are we going to do? Well, in the first step, there are two things going on there. As we move from that first augmented matrix to the second one, we're actually doing two steps at once. The two steps are, number one, we're flip-flopping the first row and the second row. They change places. That's an allowable step. And second of all, we're adding 5 times the row, that is 1, negative 2, 3, negative 1. We're multiplying that row by negative 5, multiply that by negative 5, and add it to the row that starts with a 5. And when we do that, we get a new third row that is 0, 3, negative 6, 5. And then in moving from the second augmented matrix to the third one, we're doing negative 1 times the second row and adding it to the third row. And that's going to really work on that third row, because if I do negative 1 times the second row and add it to the third row, it's going to knock out the 3 and the negative 6, because we have identical entries above and below with the 3's and the negative 6's. So we get a new augmented matrix that you see here. Now look at the triangle relative to this augmented matrix. we have 1, and then 0, 3, and then 0, 0, 0 on the bottom. Now the 3 is not a problem, because what you could do at this point is you could take the second row and divide it by 3, and that would get us a 1 there. So that 3 is not a problem whatsoever. The real problem is on the bottom where you have 0, 0, 0, especially that third 0. Because what that's saying is you essentially have an equation there, 0, 0, 0, negative 3. You're saying that if I take 0x sub 1s added to 0x sub 2s and add that to 0x sub 3s, that you get negative 3. And that's impossible because you're essentially saying that 0 equals negative 3. And 0 cannot be equal to negative 3. I mean, obviously that's a false statement. So what we have here is an inconsistent system. One final example here. For what values of h will the following system be consistent? 3x sub 1 minus 9x sub 2 equals 4. Negative 2x sub 1 plus 6x sub 2 equals h. And so we can try to reduce this into some sort of triangular form here. Okay, well, what can we do here? For starters, we could take the top row and divide it by 3. That gets us a 1 in the upper left-hand corner, which we particularly like. Then we can take negative 2 times the first row. And this is as we move from that second augmented matrix to the third one here. Take 2 times the first row and add it to the second row. When we do that, when I add 2 times the first row to the second row, 2 and negative 2 are going to combine to give me 0. Negative 6 and positive 6 are going to combine to give me 0. And 8/3 together with h are going to combine to give us h plus 8/3. Now, the first line is what it is, but that second line there is saying that 0x sub 1s plus 0x sub 2s equals h plus 8 over 3. Now, the left-hand side of that equation is clearly just 0. And so the only way that this equation can make any sense is if h plus 8 over 3 is equal to 0, and that can only happen if h is equal to negative 8 over 3.